Let's start with our next chapter, electromagnetic forces and electromagnetic induction. So what is induction? An EMF voltage is induced when a conductor moves in a magnetic field or a magnetic field changes around a conductor. If a conductor is in a complete circuit, a current is induced. So a current also can also be induced if a magnetic field moves through a static coil. As soon as the magnetic field lines of the magnet cut through the coil, the ammeter will detect a current. However, if the magnet becomes stationary, the field lines are no longer cutting through the coil and no current is induced. We have two common cases: moving wire in a fixed magnetic field. Here, wire cuts field lines and induce EMF. Moving magnet in a fixed coil. There, the field through the coil changes and it will induce EMF. No relative motion means no induced EMF. Voltmeter reads 0. Now let's talk about Lenz's law. The induced B field in a loop of a wire will oppose the change in magnetic flux through the loop. So the direction of the induced EMF always opposes the change causing it. Here we can see that B is induced and we have the V direction facing towards the current. However, here we have the direction opposite to the B induced current. So push N pole into a coil. Near end of the coil becomes N pole and it will repel magnet. Pull N pole out. Near end becomes S pole, attracts magnet, tries to keep it there. So the coil's magnetic field always fights whatever you are doing. Here we have right hand dynamo rule. You can see here our thumb is showing the motion and this finger, first finger, is showing you the field and the other one is showing you the current. Used to find direction of induced current when a wire moves in a magnetic field. So first finger, field B, points north to south. Thumb, motion of the wire. Second finger, current I, conventional, so it will be positive to negative. Now let's see electromagnetic induction. This is the demonstrating induction. Experiment number 1, magnet and coil. Set up coil plus sensitive voltmeter. Magnet is stationary, so no cutting of the field lines, no EMF. If magnet moved into coil, voltmeter flicks one way. Magnet pulled out, voltmeter flicks opposite way. Increase induced EMF by moving magnet faster, using stronger magnet, using more turns on the coil. Experiment number 2, wires between magnet poles. So we have a setup here. Long wire between magnet poles and voltmeter. Wire stationary, no induction. Wire moved across the field, cuts field lines, so voltmeter flicks. Reverse direction of motion, opposite voltmeter deflection. Increase induced EMF by moving wire faster, longer wire in the field, stronger magnetic field. Summary: factors affecting induced EMF. Size of induced EMF increases if move faster, more turns on the coil, larger area of coil, and stronger field. Direction of induced EMF reverses if reverse magnet poles or reverse direction of motion. Third, now we have AC generator. It converts mechanical energy to electrical energy, AC. Structure: rotating coil in a magnetic field. Permanent magnet provides field. Slip rings, one ring for each coil ends. Carbon brushes connect slip rings to external circuit. How it works: coil rotates, cuts magnetic field lines, changing flux, induce alternative EMF, alternating current in external circuit. Add a galvanometer, voltmeter to see needle swing both ways. Where EMF is max 0, coil horizontal moving perpendicular to the field, we have maximum EMF. Where the coil is vertical moving parallel to the field, we have 0 EMF. Graph sine or cosine wave of EMF versus time angle. Increase generator output EMF by rotating coil faster, so they will be higher frequency, more turns on the coil, stronger magnet, soft iron core inside coil. Now next we have magnetic effect of a current. Field around a straight wire. Magnetic field lines are concentric circles around the wire. Direction given by right hand grip rule. Thumb current direction, positive to negative. Fingers are the curls, field direction. More current, stronger field, closer field lines. Furthermore, wire, weaker field lines farther apart. Field around a solenoid. So, solenoid magnetic field. Solenoid is equals to long coil of wire. Field lines like a bar magnet out of north into south. Use right hand grip rule, curl fingers in a direction of a current, thumb points to the North Pole. Increase field strength. More current means more turn. And soft iron core is electromagnet. Application of electromagnet: relays, electric bells, car starter circuits, electronic locks, scrapyard cranes, loudspeakers, MRI cranes, maglev trains from earlier notes. Now, investigating field around a wire, solenoid. Tools that we have: wire, solenoid, cardboard, iron fillings or plotting compass, DC supply, ammeter, and variable resistor. Using iron fillings, place card above wire solenoid, switch on current, sprinkle fillings, gently tap. Fillings align along the field lines. This also has been discussed in our previous lectures. Using compasses, place small compass, mark direction of needle, move it around, dot and arrow. Join dots, field pattern you will get. Reversing current, reverse direction of the field, compass is turned to the another way. Now let's discuss force on a current carrying conductor, which is motor effect. A wire carrying current in a magnetic field experiences a force if current is perpendicular to the field. Reverse current or field direction, force reverses. Fleming's left hand rule: to find direction of force, first finger field B from north to south, second finger current from positive to negative, and the thumb is the motion force on wire. All three are at 90 degree to each other. Let's discuss charged particle in a magnetic field. A moving charged particle in a magnetic field feels the force at right angles to both motion and field. Max force if velocity is perpendicular to the field, no force if velocity is parallel to the field. For electrons, current direction is opposite to motion because current is in the direction of positive charge. Now let's discuss electric motor. Simple DC motor converts electrical energy to rotational kinetic energy. Structure is we have coil of wire in a magnetic field, permanent magnet, split ring commutator, carbon brushes, DC power supply. How it works? An idea is current in coil. Each slide of coil has a force, which is motor effect. Forces on opposite sides are opposite direction, which is coil turns. As coil goes past vertical split ring versus current in the coil. Forces stays in the same rotational direction, which is continuous rotation. Increase motor turning effect, speed by more current, stronger magnet, and more turns in the coil. Remember these points. Now, reverse direction of rotation by reversing current or reversing magnet poles. Now, let's discuss transformers. The structure is its primary coil, secondary coil, and it has soft iron core which can easily be magnetized. Transformers only work with AC, not DC. How a transformer works? AC in a simple coil, changing magnetic field in iron core. This changing field lines to secondary coil. It induces alternating EMF in secondary. If secondary is in complete circuit, AC current flows. Now, step up versus step down. A step up transformer increase voltage. So, Vs is greater than Vp, which means secondary voltage is greater than primary voltage. More turns in the secondary. So, Ns moves means more larger induced current. Secondary coil has more turns than primary coil. So, Ns secondary has more turns than the primary. Decrease voltage, here Vs is less than Vp. Fewer turns on secondary, which means Ns is less than Np. We have a transformer equation where Vp over Vs is equals to Np over Ns. Vp is primary voltage, Vs is secondary voltage, Np is primary turn, and Ns is secondary turn. We have an ideal transformer which is 100% efficient. Power in equals to power out. So equation will be Vp VIP equals to Vs Is. So step 1, if Vs increase, Is decrease. Step down, if Vs decrease, Is increase. We have high voltage transmission power. We have this equation and we have discussed this in our old lectures as well in of other chapters. To transfer some power with less loss in cables, use high voltage, low current. High heat loss in cables, which is equals to I square R. So lower I, much lower heating, less wasted energy. The processes in power station set up transformer, high voltage and low I for transmission. Near houses, step down transformers, low V is safer and higher I. With this, we have finished our chapter. See you in our next chapter.